January 9th, 2024, Seattle, Washington. Ross Finlayson here. Today we're going to talk some more about moment and motion. Moment and motion, these complementary concepts, which reflect both the state of things and the state of when something changes, the moment when something changes. And then as motion is generally this reflection of things that change, vis-a-vis the state, and for things that are in a state of motion. So these are the kinds of things that kind of arrive in the consideration from logical paradoxes. And the most interesting one, in a sense, is Zeno's paradox of motion. Zeno's, he has a couple different thought experiments, and they kind of arrive at why you can consider the construction of an infinite limit and get past what is otherwise an inductive impasse, and in a sense bridge the chasm as regards to deductive inference, proving how something arrives as in the middle of nowhere. And then this is fundamentally the only real fact of mathematical infinity available to our reason, which then arrives at various interesting concerns as to how to keep it so and to reveal in detail how it's so in the aletheia, or discovering, the disclosing of these kinds of things. So this is what is this usual kind of course here, and I'm kind of finding it, this is a little bit later in the evening in this far northern place where the days get short and the nights get long for about one end of the year, and on the other side being quite the opposite. So what I figured to do today was just continue to read from Berkovsky's Waves and Layered Media here that I have in front of me, and what I'm going to look for is just kind of some descriptive terms and that help just kind of explain things about waves vis-a-vis the formulaic approaches and what goes into these kinds of things. So then to reading. Where we left off is we started reading about reflections of a plain sound wave from an interface, any layer or boundary in the medium. So sometimes the layers in the media are as of boundaryless in a sense, and there's this theory about boundaries called Brentano's boundaries. So for set theory and part theory, and then there's like the idea of what's between these things, partitions and boundaries. So there's kind of like sets and parts and partitions and boundaries, and then the centers of the things. So you could kind of consider it as like a set theory and a part theory and a boundary theory and a center theory. These being just kind of the reflections of the terms that in a complementary kind of matrix fill out all the alternatives, thus offering a kind of a full complement of detail that's necessary to describe any given thing, or is sufficient. As to where sufficient is necessary. So coefficients of reflection and transmission, we shall characterize the sound field by the pressure P equals P x y z t. So this is kind of as the force, and it's also kind of is for any of these kind of surfaces, kind of the entire tendency of the surface as to have any impetus for motion, or according to potential and the law of least action, that's how it goes. In the case of our harmonic wave, an homogeneous medium, the displacement velocity of particles in the sound field is written as v, vector v, equals grad p over I to the omega p, or rho, say. Here we shall assume, as everywhere in this book, that the time dependence is given by the factor e to the negative I omega t. So this factor is for discussion before about the Eulerian and Gaussian integral analysis after the Gaussian integral, and for the Euler's identity and the particular things that it's used for as from its expressions then as in arithmetic about the addition formula, powers and sums, and mostly what's made is employed as via facts about its conjugates, which kind of just affect the sense of reflections and asymmetries that again there's definitely kind of an idea about how to, in the sense of differential geometry, where otherwise the use of the exponent or e to the for the natural constant, the natural logarithm, or sometimes called Euler's constant or Napier's constant, for the discoverer Napier of the constant in natural logarithm, or after logs and logarithm. And E, or Euler's constant sometimes, that this notion then of its phase angle and this phase, and what was the other notion? The phase and amplitude and their separation in components of transforms or as orthogonal leads to that. There's a lot of derivations built upon that, and they could be built variously for whatever else fulfills, according to a theory of types, according to a theory of equivalences, whatever else fulfills those same roles, those same goals, whatever else is sufficient with regards to necessity and sufficiency. Here we shall assume, as everywhere in this book, that the time dependence is given by the factor e to the I omega t. So within figuring out this for the angle and for time, and those being the parameter being time, and then the angle being as determined by the wave number, as noted, the derivations would so follow if to figure out a way to have a non-Gaussian Eulerian analysis of same is for like something like the identity dimension and building out another kind of complex diagram, or that there are other ways to imagine how to, for example, use when you have kind of two legs of a complex diagram either side in the fuller kind of plane, and the ability to use reversals and rotations and kind of do some bookkeeping for that part separate up front instead of as it's kind of kept in the middle, that one can imagine how to make for some other cases where it would get really, really complicated in Euler's Gaussian analysis, that it would kind of be simpler in some other notions that, again, reflect equivalent derivations. For brevity in writing, we shall, as a rule, omit this factor. Well, I guess that's keeping the units natural, where sometimes the natural units just say, okay, we're just going to leave this quantity out. It's an invariant. We're just going to call it 1. The multiplicative identity. And omit it. Let the plane acoustic wave be incident on the plane boundary z equals 0 that separates two liquid or gaseous media. The plane of incidence of the wave is coincident with the xz plane. And therefore, and here he's built these wave formalizations, and basically the direction is in y. So it's kind of as if a drawing of a thing, it's kind of like going forward, and it has above and below it in y. The plane of incidence of the wave is coincident with the xz plane. Therefore, k sub x equals k sine theta, k sub y equals 0, k sub z equals k cosine theta, and k equals omega over c, where theta is the angle of incidence of the wave, which is made by the normal to the wavefront, and the z-axis. We denote the density of the upper and lower media by rho and rho1, and the sound velocity in them by c and c1. Now, I need to check and just make sure I'm reading that letter correctly. I believe so. We now take the amplitude of the incident wave to be unity and denote the reflection coefficient of the wave by v. Then the expressions for the incident and reflected waves are written as P incident equals e to the ik in this quantity, x sine theta minus z cosine theta, and then P reflection equals v, this reflection coefficient, e to the ik, this quantity, x sine theta plus z cosine theta. So you got x sine theta plus minus z cosine theta, and as with regards to the incident and the reflection, and that's with regards to their product is the one squared minus the other squared for the great and usual facility of x plus y times x minus y. And it's discussed back in descriptive differential dynamics about when that's 1, when that's 0, as it approaches 0, as it approaches 1 from either side, as with regards to when there actually is a large coefficient in the middle, but the left-hand side is much greater than the right-hand side. And so it kind of ends up being instead just kind of like truncating that term and building up on out and in the middle parts. These are neat, usual, interesting kind of things that can be possible according to this arithmetic and algebra and ... where it's a little loose to say mathematics. But it's so. It's very rich. The refracted wave, the total field in the upper medium will be P equals P incident plus P reflective equals those two quantities. Or here as he's written it, e to the negative ikz cosine theta plus v times e to the ikz cosine theta. Instead of having pulled the terms together, he's kind of grouped them. E to the ikx sine theta. The refracted wave in the lower medium is written in the form P1 equals W e to the ik sub 1 times x sine theta 1 minus z cosine theta 1, where k1 equals omega over c1, where theta 1 is the angle of refraction and the coefficient W is known as the transmission coefficient. So here's defined that the refracted wave has the formula, what so exists is from its formula, and before and after refraction, reflection, and refraction is according to time t. So after the reflection coefficient, he says the refracted wave, where theta 1 is the angle of refraction and the coefficient W is known as the transmission coefficient. So here it's really nice that it kind of introduces, well, what's the difference between refraction and reflection, reflection and refraction anyways? And it's like, well, it's basically when that bubble of a wave hits something, it kind of bounces and squishes, and by the time it, otherwise is according to what's called the geometrical, there's optical, that generally light would similarly so behave in this manner. And so what we have is for liquids and fluids in the acoustic, these are the acoustic waves, then we'll show why that light is a different kind of model than sound, in terms of sound having a light-like model and light having a sound-like model. Vis-a-vis, for example, electricity and liquids having a fluid model, or anything having a fluid model, and then there's gases or superfluids, and solids are a particular form of subfluids, as it were, but frozen in a sense. Or is that otherwise there's these models in the middle and the models at the edges, and with respect then to how all these different aspects of the coefficients work up and out, where they're the same or where they're simply anti or opposite the other. Very usual things. The refracted wave and the coefficient W is known as the transmission coefficient. The quantities theta 1, V, and W are determined from the conditions on the boundary. These are the continuity of P and V sub Z, the component of the particle velocity normal to the boundary. The conditions on the boundary, he says, is what to define for V and W, and this theta 1, how the reflection of this non-linear thing, a wave, as its wave front passes in its travel, the formula as so parameterized by time, in accordance to its the incidence and its time and the moment, that it kind of reflects a moment of reflection. In what follows, we shall frequently make use of the concept of impedance. This says Z equals negative P over V sub Z. Since P and V sub Z are continuous in the transition through the boundary, then Z will also be continuous. We shall therefore use the boundary conditions written in the form Z equals 0, bracket of P equals 0, and bracket of Z, big Z equals 0, where the square brackets denote the difference in the values of the corresponding quantity on the two sides of the boundary. So as over this, what's like a reflection, and vis-a-vis like a symmetry and invariance and being always balanced and 0 on either side, this just kind of introduces that these quantities are the differences, and then those differences are defined in reflection of what's the impedance, is essentially what impedes the travel of the wave, or the instant of the moment where it's actually basically in the persistence of its vision before it's reflected or as it's reflected. that it's that stopping point on its way. And so this is similar in concept to the fluid model of electricity, where it's a similar notion with the various qualitative designators of what result formulaic relations, and as after parametric quantities that have then results for well-known, simple, and clear formulas as for engineering and the classical. So it results to classical. Substituting equations 2.4 and 2.5, which are the before and after, the incident and reflection combined, and then the refracted wave, we get 1 plus v, I believe that's 1 and L, 1 plus v equals w times e to the I, and this quantity k sub 1 sine theta sub 1 minus k sine theta, that times x. So then it's interesting that then this 1 plus gets into the whole roots of unity and the Gaussian and Eulerian and basically in the screw this in something that's periodic, and then if you consider periodic and also as progressing in the third dimension, the this notion that this is basically its indicator what's happened afterwards. So you might imagine as something echoes down a tunnel, it will reflect off either side and refract on its way down, and then this will add up as well in this, including keeping kind of what that is and as it echoes, and as it will attenuate and dissipate and on its way out. Since the left side does not depend on x, the right side should not depend on x either. From this we get Snell's law. K sine theta equals k1 sine theta 1. This relation expresses the equality of the phase velocities of wave propagation along the boundary in the upper and lower media. We can also write it in the form sine theta over sine theta 1 equals n, where n equals k1 over k equals c over c1 is the index of refraction, or it's on the order of, rather, is the index of refraction, that being the ratio of those coordinates before and after, as according to what's the configuration of the experiment, or the angles is incident, and the interface as basically being some point between orthogonal to the travel of the wave to parallel to the travel of the wave. Though that then it would not reflect because it would not be incident. Thus takes the form. We now return to the condition of continuity of the impedances. With the help of 2.1 and 2.5, we find the following for the impedance in the lower medium for arbitrary little z. Big Z sub 1 equals negative I omega rho 1 P1 times this quantity, partial a dP1 or by dz inverse. So the difference of position and the difference of z, that's the boundary condition, and it's also as of the side or whatever it is according to this it's in three-dimensional, this entire thing, equals rho 1 c1 over cosine theta 1, a quantity that is independent of z. In the lower medium, by using equation 2.4 for the impedance, we get in the upper medium, big Z equals rho c over cosine theta, this quantity, times this quantity, e to the negative ikz cosine theta plus ve to the ikz cosine theta. So as above, this reflects the component of the incidence, all that over this quantity, e to the negative ikz cosine theta plus ve to the ikz cosine theta. So it's only the minus version of that. So again, it's this in and out of x squared plus minus y squared, x plus y, x minus y. And this goes back to these talks in descriptive differential dynamics again about what is the what is this, and about 36 and 37 and 36 and 35 was the general idea where to start figuring out in terms of 2 and 3 and their factors and this and that, what is accordingly how to kind of grind down the squares or build up these squares in terms of running that out is a way to determine a continuous function, whereas this is kind of like stood up and saying, and it will hold up quadrature, or AKA the triangle inequality forever, vis-a-vis, and it's like, and it comes around, or as it diminishes, and these kinds of things. So that's not unusual, really. It's just not very well explored, and it's not something that people have to spend a lot of time on, because it's a bad idea to try and teach somebody some kind of really technical, yet not necessarily applicable usually, thing like the theory of magic squares and how we can model turbulences and eddy in it, or something like the yenri, the great version of the integral calculus that was invented in Japan 1,000 years ago, or in the time of the Japanese Newton, which was what we call the yenri, a whole branch and field of calculus that was not even really known in the West, and it's not really very explored in the literature. Yet still, these are the kinds of things that you can get into for particular methods. Quite a thing. And it's all about defining and resulting what implements completions for then those make for closed forms. A quantity that depends on z. At z equals 0, this should be identical with 2.12, which gives this quantity 1 plus big V times 1 minus big V equals cosine theta over rho c times z sub 1. Here is some footnotes. It has already been taken into account in equations 2.3 and 2.4 that in order to satisfy the continuity conditions on the boundary, P incident and P reflective should travel along the boundary with identical velocities. As you can imagine, there's some kind of leaps and bounds notion, or as with regards to the slinky, which would, it varies, but where it's still, there's periodic, or it's otherwise as not necessarily so constant, but constant on average, or in these kinds of things. For item second, for real cosine theta 1, the wave 2.5 gives an energy flux in the lower medium in a direction away from the boundary, as it should from physical reasoning. So this is the radiation of waves, and the dissipation and the attenuation. Here we have implicitly assumed that the propagation directions of the phase of the wave and energy flux are the same in the case of dispersive media, or C1 equals C1W. In principle, it is possible for these two velocities to have different signs. One possible example of this first was pointed out by L.I. Mandelstam. Then the field in the lower medium would have to be chosen in the form P1 equals big W e to the ik sub 1 times this quantity x sine theta 1 plus z cosine theta 1, i.e. in the form of a wave propagating from infinity to the boundary. Only in this case would the energy flux be directed from the boundary as before. So this is a great notion that kind of brings in flux, and it brings in the notion of flux that is kind of, in terms of these models, that it's one of these anti-quantities or super quantities that make a reflection for what's classical in some of these models is superclassical in some of these other models. And then as the mathematics kind of sometimes shows up that there's both sides. And it's usually just considered to pick the principal real branch and call that the classical part. And as it is the classical part. And the more footnotes, it is not necessary to give special attention to the minus sign in the definition of big A. It would have changed to plus had we chosen the opposite direction for the z-axis. So it's in as to whether it's immaterial or it's going to be as after the conjugates or some other closing the form. Otherwise, it's not a singularity, and kind of just the opposite the case we were talking about. The next footnote, in the case of an absolutely reflecting boundary, for example, for z1 equals 0 or z1 equals infinity, instead of two boundary conditions, we shall have one. P sub 1 at z equals 0 or v sub 1 z at z equals 0 respectively. Well, I'd have to understand that notation a little bit better before I can understand that. We then find that big V equals this quantity, big Z sub 1 cosine theta minus rho c over big Z sub 1 cosine theta plus rho c. So again, now we have this plus minus going on in terms of this boxing the square. This was framed in terms of a 2 by 2 square and the fact that 4's root is 2 and also its half is 2. And so a lot of stuff that goes on in terms of reflection and symmetry, according to principle, is half. And then vis-a-vis that things that algebraically involve divisors make roots. So it's the 2 by 2 square is really special in this case. This was the about the halving and windowing and boxing also. And the reading is about the Fourier integral, Fourier style analysis. And then that usually reflects notions in general senses of the quadrature, making something as of a quadrilateral, or with regards to the diagonal, or with regards to roots of 2, and these kinds of things. That 4 is the negative 2 root of 2. Roots of unity, roots of 0. How many roots are at infinity? Is it prime or composite? It varies. As we shall see in the following, this formula is valid for the reflection coefficient from an arbitrary layered half space if only its input impedance z sub 1 is found. In the very simple case of a homogeneous half space that we have considered, we find by using equation 2.12 for big Z sub 1, the coefficient, big V equals m cosine theta minus n cosine theta 1 over this quantity, m cosine theta plus n cosine theta 1, where m is on the order of rho 1 over rho, where the 1 is after and the unscripted is before. Or with the count of 2.10, that it equals this quantity, m cosine theta minus this quantity, the root of n squared minus sine squared theta. So like, again, this plus 1 minus 1 is showing up a lot. Over this quantity, m cosine theta plus this quantity, n squared minus sine squared theta, the root of that. Again, it's stacking up more. X squared plus minus 1. 1 plus minus x squared. 1 plus minus x root squared. Aw. We also noted that we denote the impedance of the incident wave by z equals rho c over cosine theta. Then equation 2.15 is written in the form v equals this quantity z sub 1 minus z over z sub 1 plus z. Again, another reflection formula. A formula, he says, that is well known for the theory of long lines, in the theory of long lines. So the long lines is with respect to transmission, and you talk about there's loss in transmission lines, there's transmission of power, and there's transmission of information or signal. And so then in these waves, then according to this transmission is basically how far the telecast will go with regards to the medium and these consequences of any loss or the attenuation and dissipation and these kinds of things with regards to the telegraph equation. But the railroad, the transcontinental railroad was accompanied with the transcontinental telegraph, and then sometime later when they sank their first transoceanic cable from England to the United States it revolutionized telecommunications and over the border wireless or over the border realer time communications. Let us consider some special cases. For normal incidence of the wave on the boundary, theta equals theta 1 equals 0, we have v equals m minus n times n plus n equals rho 1 c1 minus rho c over rho 1 c1 plus rho c. So just the product of the coefficients before and after, their sum and their difference. For grazing incidence, so this is grazing is when the angle is small. It's when the reflection will be very obtuse vis-a-vis the reflection being direct or backwards. For grazing incidence and limit as theta goes to pi over 2. So here it says as when the angle is large, we obtain v goes to -1. Then as with regards to measuring the other kind of angle, as we were talking about and reading about the sum of interior angles from Wertheimer, gets into these reflections, the opposites, and why then all these kinds of things, for example, to do with linearizations and this and that, can be built either or in both ways if they're kind of kept up correctly all not throughout. For an angle theta, which satisfies the condition m cosine theta minus this quantity, n squared minus sine squared theta, that root, equals 0, the reflection coefficient vanishes. This is the case of complete transmission at the boundary. Aha, so here this helps reflect that when something has any matter of reflection and refraction, that then it's not completely transmission. So you can think about the opaque and the transparent, and here the transparent and the translucent, anything in between, with when the reflection coefficient is maximum or when it's minimum in a sense. This is a case of complete transmission at the boundary. From the latter quality, we find for the angle of complete transmission, sine theta equals this quantity root of this quantity m squared minus n squared over this quantity m squared minus 1. So now it's getting pretty interesting, because we start working with two of these halving boxes with windowing and boxing, and about the roots of 2 and the negative powers thereof in a sense, and this is just something that could be kind of built all together and relate these things, and it's something that, according to arithmetic, first of all this stuff kind of follows out from arithmetic and just manipulating the expressions and equations these ways according to their derived and defined quantities. They're defined and then derived further, and then with regards to their systems, what maintain the conditions, that is really quite a thing. And they're familiar to anybody who knows arithmetic, and a lot of these most simplest laws of the factoring of monomials to make polynomials, and then it gets into all kinds of things about methods that can make for replacing such simple as notions of this with entire complete infinite expansions in the middle. It could be quite profound to figure out how to represent what are quantities in these sorts of derivations, and that the derivations would stay the same throughout by finding the right tracks and channels, just to write out an expression that can then be implicit. Maybe it just is. I mean, maybe there's these same formulas are designed especially to keep these particular spare geometric forms, or algebraic forms, excuse me, I suppose, and that then would so follow that by imbuing the implicits of the definitions, that stronger results carry forward, or that more tractability comes forward from just simply expanding the context while having these being some kind of normal forms. That would have to be explicit, though, to not be implicit, of course. So, in the case of equality of the velocities, c1 equals ct. Now I skipped a bit here. Quite separate from any relation of the parameters of the media, theta in 2.19 will be a real angle. For this case, as is seen from 2.19, the satisfaction of the condition 0 is less than equal to this quantity m squared minus n squared over this quantity m squared minus 1 is less than equal to 1 is necessary. So here, as we've been talking about the boxing the squares and this kind of stuff, is that now it's some further bounds been put on it, so even more and better conditions can be said to hold up. And in terms of here, it was the hyperbolic. So the differential descriptive dynamics has a lot of interesting notions that would end up being developed quite a bit more fully and thoroughly. They were really just kind of in a happenstance manner encountered in the readings. And some kind of inclination to impress or something, I suppose. It then follows that for m greater than 1, we must have 1 less than n less than equal to m. And for m less than 1, we require 1 greater than n greater than equals to m. And so this then reflects onto our systems of inequalities and how those establish these transitive relations on as through these. So then, in according to the bounds being one or the other, you can say that everything is inside the box. In the case of equality of the velocity, c1 equals c3, n equals 1, the reflection coefficient turns out to be independent of the angle. V equals rho 1 minus p over rho 1 plus p. Harmonics. See, section 2.2 here has total internal reflection. So we kind of have read through this section 2.1. So I'm going to mark this here kind of and kind of look around here a bit. He talks about the caustic. And what I wanted to do was take a look at now this light book that has to do with multiple beam interferometry. So interferometry is kind of like you use the properties of light and its refraction according to use that as measuring devices for things that are small and as in gratings or as in the media and these kinds of things. So let's see if this is very near the top of the stack. Because otherwise, well, what I might do is take a look here at Eric Temple Bell and see what he has to say about reflection and refraction. So this book is Eric Temple Bell's Metamathematics. It's a biography of a bunch of the most famous mathematicians according to the Western tradition today. So he says, Zeno, Eudoxus, Archimedes, Descartes, Fermat, Pascal, Newton, Leibniz, the Bernoullis, 8 mathematicians in 3 generations, Euler, Lagrange, Laplace, Monge, Fourier, or Monge, M-O-N-G-E, he's a Frenchman, Poncelet, Gauss, Cauchy, Lobachevsky, to these days often written Lobachevsky, Abel, Jacobi, Hamilton, Galois, Sylvester, and Cayley, Weierstrass, Boole, Hermite, Kronecker, Riemann, Kummer, Poincaré, Cantor, where he closes, Jörg Cantor. Poincaré is great. He really is complimentary, Poincaré. Anyways, this book was published a long time ago, so its style is a little dated, 1937. This book was published much later, but this printing of it. And Bell is readable. It's quite eminently readable, and it's an interesting perspective on the lives and kind of how they came together and lived in the same world, and what results today that there are these things and as they've so arrived as our canon. It's canon. Take a look at that. So, excuse me here. What is this? What I got here is that I'm looking for waves, light waves. Oh, I think I found it here. One moment. This will do. Okay. So, this is multiple beam interferometry of surfaces and films. And this book is called Dynamic Light Scattering. And so, with applications to chemistry, biology, and physics. So, the idea is that in terms of luminescence and what can be done in terms of everything from like gel electrophoresis, that's not really an application of scattering and light and interferometry. But then there's stuff like the, what would you say? The mass spectrometer, or from that to all kinds of like scatter counting, scintillation counters, or other things where, or like lasers. Anything that has to do with that kind of stuff can be pretty relevant and interesting. So what I was just curious to see if I can find something kind of briefly about reflection and refraction with regards to light, because light, unlike the acoustic, kind of has refractions kind of all the way out of it, it's optical. So as before, we're talking about the incidence of reflection as being essentially geometric, and as with regards to the classical, just like a billiard ball bounces off the bumper and essentially reflects, that its angle of reflection is its angle of incidence. That its refraction is essentially as if the ball is spinning at an arbitrarily high velocity, and thus that the way that when at this moment when it actually collides, and it's deformable and it's elastic and it's compressible, then you can basically affect that a given pool shot, or in billiards, this game, there can be any arbitrary incident angle and any arbitrary reflection angle. But for light, because that's controllable, for light, the idea is then that it's actually got arbitrarily high rotation associated with it. And that's its nature. It's part of its model of its behavior as a wave. Among all these other things that behave as waves, that they have wave models, then it's just insofar so much so much more that it has its supermodels. This book stresses the use of light scattering to study the time dependence of thermal fluctuations in fluid systems. Since time correlation functions are usually used to describe these fluctuations, the book should also be useful as an introduction to the theory of time correlation functions. So this is one of the few words that I associate now with flow, our propagation equations, and flow and flux, that which flows out, or the fleeting, and fluctuations with regards to Poincaré's rough plane and Euclid's smooth plane, and with regards to Born's restless universe and the vague fugue. Simmering, say. Which for some is like, at a low boil or almost at a boil. And for others is kind of a medium boil, and it kind of depends. This is not a roiling boil, say. Descriptive terms. Electromagnetic radiation is one of the most important probes of the structure and dynamics of matter, says Bruce Byrne and Robert Pecora. The absorption of ultraviolet, visible, infrared, and microwave radiation has provided detailed information about electronic, vibrational, and rotational energy levels of molecules, as has in some instances enabled the chemists and physicists to determine the structure of complex molecules. Scattering, tunneling, electron microscope. The original STEM, Radio frequency spectroscopy has had an enormous impact on solid-state molecular physics and physical, inorganic, and organic chemistry. The structure of solids and biological macromolecules has been elucidated by X-ray diffraction experiments. Raman scattering is another spectroscopic technique that provides information similar to that of absorption spectroscopy. When photons impinge on a molecule, they can either impart energy or gain energy from the translational, rotational, vibrational, and electronic degrees of freedom of the molecules. They thereby suffer frequency shifts. Thus, the frequency spectrum of the scattered light will exhibit resonances at the frequencies corresponding to these transitions. Now, it uses the word suffer, and it's not to be meant that they so much lose anything. It's just that it's the state of them together. That's all it is. This book deals only with the characteristics of the light scattered from translational and rotational degrees of freedom. That is, with what is now commonly called Rayleigh scattering. So here we have, in the waves, we're going to get into the descriptive, and Rayleigh, again, is really involved with these waves. And here with Rayleigh scattering, and as for later there'll be Raman scattering, but for the scattering and tunneling, where those are the theories as part of quantum mechanics that explain the propagation of things, that then Rayleigh is also associated with Rayleigh genes very closely with the ultraviolet law and the ultraviolet catastrophe, and what's associated with electron physics that makes modern physics today, and why Einstein's photon to electron ratio was so great, and that it ended up resulting that electron physics made for particle physics a computational milieu and a classical formulation. And then as with regards to the real parts that they're left out of that are empirical yet, that Rayleigh is going to be up there with Fresnel among the people who I think know the most about light. Recent advances in laser techniques have made possible the measurement of very small frequency shifts in the light scattered from gases, liquids, and solids. Superfluids, liquids, fluids, and frozen fluids. For example, or is any in the model of each other, like except for solids kind of have this entire stateful apparatus. It's like they don't flow, they don't float, they don't have, they're not solvents or solutes, whereas gases and liquids are kind of interchangeable. And usually it's for pressure, it's gas models vis-a-vis the compressible. And then otherwise that for continuum mechanics, it's usually the fluid models because it's incompressible and reflects that sort of conservation. Moreover, because of the high intensities of laser sources, it is possible to measure even weakly scattered light. Thus, the main difficulties in performing light scattering experiments encountered in the past are eliminated when lasers are used. This explains the rather remarkable proliferation of laser light scattering experiments in recent years. The structure and dynamics of such diverse systems as solids, liquid crystals, gels, solutions of biological macromolecules, simple molecular fluids, electrolyte solutions, dispersions of microorganisms, solutions of viruses, membrane vesicles, protoplasm in algae, and colloidal dispersions have now been studied by laser light scattering techniques. When light impinges on matter, the electric field of the light, well, I don't know about that. You got the optoelectronic effect, but see. The electric field of the light induces an oscillating polarization of the electrons in the molecules. So here it's just kind of reflecting that just like there's a kinetic interface to the nuclear, then there's just kind of this optical interface to the charge. But not all materials are as regards to affecting electron transport from light, nor is for all kinds of light. The molecules then serve as secondary sources of light and subsequently radiate scatter light, or as energy in the format which it is, but usually as transmission, yes. The frequency shifts, the angular distribution, the polarization, the intensity of the scattered light are determined by the size, shape, and molecular interactions in the scattering material. Thus, from the light scattering characteristics of a given system, it should be possible to aid of electrodynamics and theory of time-dependent statistical mechanics to obtain information about the structure and molecular dynamics of the scattering medium. The basic theory of Rayleigh scattering was developed more than a half century ago by Rayleigh, Smolichowski, Einstein, and Debye, who's also very famous, Debye, Debye. It is well worth summarizing some of the high points in the history of the field. Since the experimental studies by Tyndall, 1869 on light scattering from aerosols, and the initial theoretical work of Rayleigh, 1871 and 1881. Light scattering has been used to study a variety of physical phenomena. These studies considered scattering from assemblies of non-interacting particles sufficiently small compared to the wavelength of the light to be regarded as point-dipole oscillators. In his 1881 article, Rayleigh also presented an approximate theory for particles of any shape and size having a relative refractive index approximately equal to 1. Now, this notion of the system, kind of like a photosystem of a plant that performs photosynthesis, or this point-dipole oscillator is a system, or atoms in chemistry, is that they're arbitrarily small cellular automata. So, two people who you'd be familiar with theories of cellular automata include Stephen Wolfram. He's got his whole rule 85 or whatever, what he's trying to work out with his new kind of science. And John Conway, who invented, he's very familiar for games of cellular automata, like the game of life, and basically on graph paper that you have a rule for each pixel, and so you can define rules that make flyers and gliders and these kinds of things. And he's also familiar for a non-Archimedean field he named the surreal numbers, which is considered a conservative extension of the Archimedean complete order field, if there is such a thing. And then also most famously his book with N.J.A. Sloan called Lattices and Sphere Packings, about how many apples and oranges fit in a box, which is very difficult to figure out, but it's very interesting, and would have a lot to do with respect to all these kinds of things in the models of the things, the gases and liquids and solids in their forms of the colloidal or the crystallographic. So anyways, that's just to reflect that there's all kinds of ways to take these elementary sorts notions of motions and moments in motions, and as they reflect then media and matter in media. In his 1881 article, Rayleigh also presented an approximate theory for particles of any shape and size having a relative refractive index approximately equal to 1. Rayleigh, 1899, explained the blue color of the sky and the red sunsets as due to the preferential scattering of blue light by the molecules in the atmosphere. In subsequent papers, Rayleigh 1910, 1914, 1918, Rayleigh derived the full formula for spheres of arbitrary size. For these larger particles, there are fixed phase relations between the waves scattered from different points of the same particle, but each scattering element of the particle is regarded as an independent dipole oscillator. Debye, 1915, made further contributions to the theory of these large particles and extended the calculations to particles of non-spherical shape. Gans, 1925, also contributed to the theory of large particles of relative refractive index approximately equal to 1. Theory of such particles is often referred to as the Rayleigh-Gans theory. According to Kircher, 1969, Gans's contribution to this method was hardly significant. It seems more appropriate to call it Rayleigh-Debye scattering. Well, priority. Those are matters of priority. Who's said to have what? And so sometimes it's equipped to the person who's less famous, the result, because the famous person has a ton of other results to disambiguate already. But for these corner type cases, it's like, this is so-and-so's result. Because Debye has a lot more going on. In large particles of relative refractive index, much different from 1, there are not only fixed spatial relations between the scattering elements, there's also a strong independence of the electric field amplitude on the position of the particle. So this is usually called static potential. These are there are formidable theoretical problems associated with the treatment of these large particles. Only for the case of spheres does there exist a complete solution. Me, 1908, and independently Debye, 1909, solved this problem. This type of scattering is now referred to as me scattering. These problems were discussed at great length in the monographs of Van Holst, 1957, by Kircher, 1969, and are consequently not considered in this book. Studies of the angular dependence and polarization of the scattered light are now routinely used to study the shapes and sizes of large particles. Millimeter wave, all this kind of stuff. Although Rayleigh had developed a theory of light scattering from gases with some success, it was soon found that the intensity of scattering by condensed phases, molecules per molecule, was less than that predicted by his formula by more than 1 order of magnitude. This effect was correctly attributed to the destructive interference between the wavelets scattered from different molecules, but unfortunately the means of calculating the extent of this interference was not known at the time. Smoluchowski and Einstein elegantly circumvented this difficulty by considering the liquid to be a continuous medium in which thermal fluctuations give rise to local inhomogeneities and thereby to density and concentration fluctuations. These authors developed a fluctuation theory of light scattering. So here that's attenuation and dissipation, or that's basically it. And then it goes into some of the particulars of why they arrive at what they consider as the first approximations, or the first approximate forms on the order of that they attribute given things according to inverse square, or on the order of these other terms with regards then to the notions of coefficients, and then with regards to constants, coefficients, and then with regards to whether they're running constants, and then as regards to these terms and their formula. So let's see here. So we talked a little bit about reflection and refraction, and this is about multiple beam interferometry of surfaces and films. This book by Tolonsky was a whole $3. Dover reprints many books at a very, very fair price. In 1948, but this is from 1970, of the original published in 1948. Optical interference techniques, high magnifications, high resolution, 5 astronomical units. Although recent elaborate electron microscope stereoscopic methods claim to measure heights of the order of 100 AU, this gets into a variety of lab techniques describing two-beam interference, multiple beam interference, a silvering technique, silver modified Newton's rings, crystal topography using Fizeau fringes, quartz mica selenite calcite, crossed Fizeau fringes diamonds, doubly silvered films, Fizeau fringes of equal chromatic order. So Fizeau and Fresnel are pretty close, and Fresnel was more the theory, and Fizeau is really the lab guy. Applications of fringes of equal chromatic order, mica surfaces, observations on thin mica sheets, study of a range of mica samples. So mica is a naturally occurring material that's very regular in its crystallographic structure. So it has very many good properties for heat resistance and these kinds of things. Further applications: opaque substances and metals, plastic replicas, interferometric color filters, and monochromators, non-localized multiple beam fringes. So this gets in a lot more of methods, but the designs and what they reflect would also present the setups and ansatz for lots of then different kinds of approaches to formulaic experiment and theoretical confirmation, or the lack of rejection thereof, falsifiability. Well, that's that, for the time of day. It's as you can tell, it's pretty dark by now. And, there's not much more to be said for what remains of the day. What I should so hope is that the wind doesn't blow the city down and knock power out for everybody. It's a nice little blizzard coming up, or it's the storm of 2024 in the winter. I mean, and who knows what it'll be like in the summer because of, record high temperatures everywhere. But we'll see how that goes. So anyways, I hope you have a great day. And what we read about today was we read section 2.1 of Braikovsky's, and we talked a lot about how it gets into these forms, what reflect in the algebraic and arithmetic, what essentially are then these geometric. And then about the very particular case, how the algebraic and the arithmetic kind of stays around the corners and stays around on the sides, vis-a-vis what's this refraction, and then for the optical, and then these various models, how that gets out into the nonlinear and diffraction and these kinds of things, about all these kinds of things. So I hope you have a great day, and so long.